A groundbreaking approach to heating Mars has been presented by scientists. Greetings everyone. Today's video topic revolves around a groundbreaking idea put forth by researchers from the University of Chicago, Northwestern University, and the University of Central Florida. They have presented a revolutionary technique for terraforming Mars, involving the release of engineered dust particles into the planet's atmosphere. This innovative approach has the potential to raise Mars's temperature by more than 50 degrees Fahrenheit, thereby creating a suitable environment for microbial life. Unlike previous proposals, this method is remarkably efficient, surpassing them by a factor of 5,000, and it relies on resources readily available on Mars. While it may not directly result in a breathable atmosphere for humans, it could serve as a crucial step towards future habitation by augmenting Mars's natural greenhouse effect. Without further delay, let us begin our discussion. A team of researchers from the University of Chicago, Northwestern University, and the University of Central Florida have recently presented a groundbreaking study in Science Advances. Their study introduces a revolutionary technique for terraforming Mars, which involves the release of engineered dust particles into the atmosphere. This innovative approach has the potential to raise the temperature of the red planet by over 50 degrees Fahrenheit, creating an environment conducive to microbial life. This significant development marks a crucial initial stride towards transforming Mars into a habitable planet. In terms of efficiency, the proposed method for globally warming Mars surpasses previous schemes by a staggering factor of over 5,000, signifying a remarkable advancement in our capacity to manipulate the Martian environment. The distinguishing factor of this approach lies in its utilization of the readily available resources on Mars, rendering it considerably more viable than previous proposals that relied on importing materials from Earth or extracting scarce Martian resources. While it may require several decades to implement, this particular approach seems to be more logistically feasible compared to alternative proposals that have been put forward thus far. According to Edwin Kite, an associate professor of geophysical sciences at the University of Chicago and the study's corresponding author, this indicates that the obstacle preventing Mars from warming enough to sustain liquid water is not as formidable as it was once believed to be. The primary author of the study was Samaneh Ansari, a graduate student in Professor Houman Mohseni's research team at Northwestern University. The ability for astronauts to breathe the thin air on Mars remains elusive, as significant efforts are required to render the planet suitable for human exploration without the need for assistance. However, it may be possible to lay the groundwork by creating an environment that supports microbial life and cultivates food crops, gradually increasing the oxygen levels in the atmosphere, much like the processes that have shaped Earth throughout its geological past. Throughout history, numerous proposals have been put forth to make Mars habitable, including a concept devised by Carl Sagan in 1971. These ideas have spanned from fantastical daydreams, such as transforming one of Mars's moons into a sun, to more recent and scientifically feasible concepts, like developing transparent gel tiles to capture and retain heat. When considering the goal of transforming Mars into a habitable environment, there are numerous challenges that need to be overcome. These obstacles include the presence of harmful UV rays and soil with high salt content. However, the most significant hurdle is undoubtedly the extreme temperature on the planet, with an average surface temperature of approximately -80 degrees Fahrenheit. An approach to increasing the temperature of Mars could involve utilizing a similar technique inadvertently employed by humans on Earth: the deliberate release of substances into the atmosphere, thereby amplifying the planet's existing greenhouse effect and effectively capturing solar heat on its surface. The challenge lies in the fact that a substantial quantity of these materials is required, quite literally. Past strategies relied on transporting gases from Earth to Mars or extracting a significant amount of uncommon ingredients from Mars itself, both of which are expensive and challenging endeavors. However, the team pondered the possibility of achieving this by utilizing the abundant materials already present on Mars through a processing method. Through the exploration conducted by rovers such as Curiosity, it has been established that the dust present on Mars contains significant amounts of iron and aluminum. In their natural state, these dust particles do not possess the capability to heat up the planet. In fact, due to their size and composition, they have a tendency to slightly cool the surface instead. However, researchers have proposed the idea that by altering the shape or composition of these dust particles, it may be possible to enhance their ability to effectively retain heat. Particles resembling small rods, comparable in size to glitter that can be found on the market, were meticulously crafted by the researchers. The purpose of these particles is to capture and confine heat that would otherwise escape, while simultaneously redirecting sunlight towards the planet's surface. This ingenious design amplifies Mars's inherent greenhouse effect. The interaction between light and objects that are smaller than the wavelength of light is truly captivating. It is worth noting that the field of engineering plays a crucial role in understanding and manipulating this phenomenon. The utilization of nanoparticles can result in optical effects that surpass the conventional expectations by a significant margin. We have only begun to explore the potential of these minute particles, Ansari stated. Mohseni, also a co-author, expressed optimism about their research. Our team is confident that we can develop nanoparticles that are even more efficient and possess the ability to adapt their optical characteristics. According to Kite, the amount of millions of tons required to heat up the planet is significantly reduced by a factor of 5,000 compared to previous ideas for warming Mars. This substantial decrease in quantity greatly enhances the practicality of the endeavor. If the particles were continuously released into the atmosphere of Mars at a rate of 30 liters per second, calculations suggest that the planet's temperature would increase by over 50 degrees Fahrenheit. This significant warming effect could be observed in a matter of months. Furthermore, the warming would be reversible and would cease within a few years if the release of particles was halted. However, there are still many uncertainties that need to be addressed. For instance, it is unclear how quickly the engineered dust would dissipate from Mars's atmosphere. Additionally, Mars possesses water and clouds, and as the planet warms, there is a possibility that the particles could cause water vapor to condense and precipitate back to the surface as rainfall. Kite warned that accurately modeling climate feedbacks is a challenging task. In order to successfully implement a plan like this, it would be necessary to gather additional data from both Mars and Earth. Furthermore, a cautious and gradual approach would need to be taken to ensure that the desired effects are achieved. Although this approach marks a notable advancement in the field of terraforming, the researchers stress that their study primarily concentrates on raising the temperature of Mars to support microbial life and potentially cultivate food crops, rather than focusing on generating a breathable atmosphere for human habitation. Kite expressed that this research presents exciting opportunities for further investigation, potentially advancing us towards the cherished goal of establishing a sustainable human presence on Mars. Leading the study is Ansari, with Ramses Ramirez from the University of Central Florida and Liam Steele, previously a postdoctoral researcher at UChicago and currently affiliated with the European Centre for Medium-Range Weather Forecasts, serving as co-authors. The Quest High-Performance Computing Facility at Northwestern and the University of Chicago Research Computing Center were utilized by the authors. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.